we use the fact that we have two force members, three force members, or two force and a moment member. If you do that, things become much, much simpler. Well, let's draw the free body diagrams again for each of these members. So this is link 2, this is link 3, and this is link 4. Now, well, think about link 3 first. This angle is, by the way, let's say this is theta 1, 2. This is 3. But theta 1, 3 is a, it's a long angle. So let's use alpha here. Alpha is theta 1, 3 minus pi minus theta 1, 3. Now, what are the forces on the link 3? There is one force on one side, there is another force on the other side. So how many forces are there? Two forces. So this is a two-force member, right? This is a two-force member. But how can the forces be if it's a two-force member? They have to be equal in magnitude, opposite in direction, right? They cannot be anything else. So the force has to be in this direction. There is no other possibility. The F2, 3 has to be here. Okay, but it can be, we assume something. We assume that it is in this direction, but its direction, we assume that it is compressing the member, but you can assume that it is tensile also, but it's definite that it's along the direction of the link. And if it is so, the other force, which is F43, has to be in the direction of the link as well. We understand this. This is a two-force member. Therefore, the forces have to be equal in magnitude, opposite in direction, and they have to be along the link. If they are in some other direction, it's not possible because they will have a couple effect. If you had something like this, any force that is like that would have a couple effect on the member. So they shouldn't have a couple effects. So that's the only possible solution. So F43, so we have F43 and also F23. This is the force applied by link 2 on 3. Now, forces are equal in magnitude, opposite in direction. This means that F32 is equal in magnitude, opposite in direction, acting on link 2. F32 is in this direction, okay? Well, we know that there is T12, we don't know this. But what kind of number is this one now? Well, there is a force here. There has to be a force here as well. But this force has to be opposing F23, right? It has to be something like this. Supposedly this has to be parallel to F23. So this is G12. As we know, G12 and F23 have to be equal in magnitude, opposite in direction. This is a two force plus one moment number, as you can guess. Okay. So there is a moment effect of those forces. And these forces, although it looks like this is not a 90, this is not a right angle, okay? The forces do not make right angles with our member. This is just an illusion, or it's because of my drawing. Okay, how about this one? The third one, F43, F43, acts the force on 3, 4 because 3 because of 4. It has to be a equal and opposite force, F34, like this. That has to be, right? There is F14 force. And there is the G14 force. If G14 just everything passes from point B, then this is a 3 force member. Or you can have the following. If G14 you assume acts somewhere else, now this distance we would call it A, in which case we would say that M14 is equal to A times G14. That is, if you relocate G14 to here, there is no need for M14, so this is a 3 force member, as you see. Okay. So, as we see here, let me try to open up some space by erasing these. Okay. So each of these members are like this. Now, for link 2, we have it's a 2 force plus 1 moment member. As we see, the magnitude of G12 has to be equal to F32, magnitude of F32. Their directions are opposite, but it doesn't matter. Now the torque P12 has to be equal to perpendicular distance, whatever that perpendicular distance is. We will find it out. Okay, it will be something like this. This almost looks perpendicular, but it doesn't have to be. So this is H. Okay. P12 is equal to H times, well, G12 or F32, the magnitude of the force. Okay. Okay, so we write these equations. For link 3, this is a 2 force member. Okay, we have F23 is equal to F43 magnitude wise, and that is equal to F34. And as a matter of fact, this is equal to F32 also. Okay. Okay. Ring 4 is a 3/4 member. So, for example, the forces have to be, well, add up to 0. This angle we have called alpha, which we kind of know. As you know, here you can say that F34 cosine alpha is equal to F14. Okay. So you can find that F34 is equal to F14 over cosine alpha. And we know that this was known. Okay? It is given that it is known. So it is F14 divided by cosine. Alpha is pi minus theta 1, 3, right? So F34 is known now. If F34 is known, what else is known? F34 is known, this is known, this is known, this is known, this is known now. This is known. The only thing is this h distance. Therefore, well, how can I write it here? You can say that T12 is equal to h times F32, but F32 is equal to F34, which is F14 divided by cosine pi minus theta 1, 3. Okay. Actually, if you do this, if you open up cosine theta pi minus theta 1, 3, you will find that this is equal to cosine theta 1, 3. So this is h times F14 over cosine 3. Then the only thing that is unknown is h, which we will find out. H is not too hard to find, actually. So as you see, we almost solved it, okay, except for that perpendicular distance h, which I couldn't really show very well. So using the fact that we have two force members, three force members, etc., we got a very quick solution. Instead of solving 13 equations, we kind of got a solution rather quickly. Well, we didn't get it completely yet, but we almost are there. Okay. Oh, by the way, we have something important here. I want to make note of it here. We have to spend some time on this. Now, this is kind of important because we will use it quite often. Let's say that you have a link like this. Okay. And on this link, let's say this is point O. Let's say this is point alpha. And there is a force acting on it, F. Okay. Now this link is represented by a vector R. Well, we want to find the moment of F about O, which is MO, which, as you know, is R cross F. Right? This is the definition of the moment. Now we want to derive an expression for this. This F force, let's say it makes an angle beta with the horizontal. And also, let's say that the unit vectors along the R and F directions are U and V. U and V are the unit vectors. So that we can write R is equal to magnitude of R times U, and F is equal to magnitude of F times V. Okay. We say that U and V are units. Okay. So the moment about O is R cross F, which is R cross F, which is RU crossed with FV, which is RF times U crossed with V. But what is U and V? If they are unit vectors, U has to be like cosine alpha I plus sine alpha j, right? And V has to be cosine beta I plus sine, as you can guess. They are, these are the projections of unit vectors along x and y axis. So if you do this, U crossed with V will give you, well, cosines and sines. If you multiply them, you can do the multiplication yourself. I cross j is a k, I cross I is a 0, j cross I is a minus k, etc. So U cross V is going to give you the following: cosine alpha sine beta minus cosine beta sine alpha in parentheses of k. K is the vector in the page. K is the vector coming out of this page. Okay, so it is like this is I, this is J, this is K. Well, using trigonometric identities, this is cosine sine minus. So this is sine alpha minus beta. Okay. So we get an important result here, that the moment about O is equal to RF times sine alpha minus beta. This is something we will use quite often. Okay? Just keep this in mind because it's an important and necessary result. Now this has to do with our problem. Remember, we wanted to find this h distance, or well, the moment arm of this F32. We wanted to find the moment of F32 about θ12 actually. As a matter of fact, it is as follows. Let me draw it here. Beta minus alpha. Yeah, that's right. Why did I? Actually, it is so in my notes, but I somehow wrote alpha minus beta. This is beta minus alpha. Thank you. Okay. So we have, in our case, something like this. Or maybe I should draw it like this. F3, 2, and the angle it makes with the horizontal is theta 1, 3, as you know. And this angle, this is point O. This angle is theta 1, 2. And this is exactly what we have. This is A2. We want to find the moment arm of this force about point O. Okay, moment of this force about this point. So the moment is equal to MO of this force is equal to F32 times A2 times sine. I don't have space there. Sine theta minus R, which is theta 1, 3 minus theta 1, 2. Right? And this is equal to theta 1, 2, as you know. This has to be, because this force has to be counteracted by theta 1, 2. Okay. Well, maybe I should say minus T 1, 2 is equal to 0. Okay. This is the moment of this force. So T1, 2 therefore is equal to A2 times F32. But F3, okay, let's start F32 sine theta 1, 3 minus theta 1, 2. But from the previous page, remember that, what was it? F34, F32, etc. is F14 divided by cosine theta 1, 3. So we have A2 times F32 is equal to F14 over cosine theta 1, 3. And you have sine theta 1, 3 minus. And this is the solution. This is the result. Okay. As you see, we have found a closed form solution for the slider crank mechanism, torque of the slider crank mechanism. This is true for all lengths, for all angles, etc. Okay. Given F14, you can find T12 if you assume static force analysis. Well, if you assume that the forces are static. Okay, there is no inertia force. And this is true for internal combustion engine, for example. The torque developed by the internal combustion engine is given by something like this. So, for example, if theta 1, 3 is equal to theta 1, 2 somehow, then the torque developed is 0. I don't know how this happens. Okay. So this is how we usually solve our problems. We solve our problems using the fact that some members are two force members, some members are three force members, some are two force and a moment member, so that the equations become much simpler. As a matter of fact, I can say that the following. If you have a two-force member, you have no equations to solve. Okay, because graphically you have, well, written everything. If you have a two-force and one moment member, you have one moment equation. If you have a three-force member, you have two force equations. As a matter of fact, in this case, for example, for this one, the fourth member, we can find G14, for example. We didn't really care about finding G14, but we could have found it, saying that this is F34 divided by, well, it is F34 sine alpha, right? Yes. If it's a three-force number, you have two force equations. Well, if you have a three-force and a moment number, if you assume that the G14 acts at a certain distance, then M14 will be dependent on G14. That's another thing. So remember that we have these equations. We have to write these equations when necessary. Okay, let me start, since we have started with a slider crank, our next mechanism is the 4-bar, as you know. Let me solve a 4-bar. Let's suppose that some force acts on this 4-bar mechanism like this, and it makes an angle of theta with the horizontal. So it is called F13 for some reason. This is supposedly this is known. Okay. And there is a torque to the force, the moment, which we want to determine, that is unknown. The location of action of this force is supposedly known. You can say that the distance is like d3 or something. So that, let's say this distance is, it's hard to show it here. Well, anyway, let's say that this is a B. Let's say that this is C. C point is known. So let me not just complicate the matters. Okay, now what do we know? We have to start drawing by drawing free body diagrams as usual. Second link, third link, fourth link. Let's see. So what do we know? Well, we can start from the fourth link, I suppose. That's the easiest one. What do we know? Well, there are forces at both ends of this link, here and here. So what kind of link is this? It's a two-force number. I say that F34 force on link 4 due to link 3. Well, let's assume that it is in this direction, by the way. We don't know the direction, but we assume that it is outwards, let's say. If it's outwards, this has to be outwards as well. This is G14, right? F34 is in the following direction. Well, we kind of know the directions because the angle is known. This is theta 14. So that F34 as a vector, we can write that F34 is a vector is equal to F34 magnitude times, not times, but rather with an angle of theta 14, right? F34 has an angle of theta 14, which we can write as, cosine theta 14I times sine theta 14J. Okay, so it's a two, we know that this is a two-force number. Link 4 is a two-force number. How about link 3? But if F34 is in this direction, then F43 has to be equal in magnitude, opposite in direction. Okay, we know that much. We also know beta. We also know, the force F13, whatever it is. F13 makes an angle of beta. Now, F23. There is another force here. We don't know it, but we know that there are three forces here, right? And these forces somehow have to meet at a certain point. How can that be? So this is as you see, this is a three-force number now. How can it be? For example, might be that it is this. 2, 3. Yes.
F13 input force.
F13 is input, it is known. This F23, we don't know what it is, and we don't know its angle, but we know that it's a 2-force number. Sorry, this is a 3-force number. Let's say that it has an angle of alpha. Let's say that F23 as a vector is equal to F23 with an angle of alpha. Alpha is unknown, but it can be found because well, all these forces have to coincide at a certain point geometrically, or the summation of these 3 forces have to add up to 0. Okay, and their moment effect is going to be exactly 0. Okay? Or we can kind of take a moment of 2 forces, and we will find that that moment has to be 0. Anyway, so if this is F23, then on link 1, you have link 2, I'm sorry. This is link 3, this is link 4, this is link 2. You have F32. Well, you also have P12. This is a 2-force and a moment number, as you see. What do you have here? It has to be a parallel thing. Supposedly, this is parallel to this is Z12, and Z12 also has an angle of alpha, as we know. Okay, well, I think we are getting late, so let's take a break here. We will continue from this point on. So let's stop for about 10 minutes. So F34 can be written in the phasor form. G14, for example, can be written, sorry, not like this, as a vector. It is G14 magnitude. Its angle is this whole total angle, which is theta 14 plus pi, as you can guess, right? It is, you add a pi angle to this. This is pi. It's not very important, but just to show you how it is. This angle is theta 14. Now this F43 is equal to F43 magnitude with an angle of theta 14 plus pi again, right? It has to be in the same direction with theta 14. F13 is equal to F13 with an angle of beta. We know this much. F23 is F23 alpha. F32 is what will that be? F32 with an angle of alpha minus pi, I suppose. Or you can, it doesn't really matter. You can even say alpha plus pi. Minus pi and plus pi gives you the same thing, isn't it? Let's use plus pi. Because you make an angle of pi again, you come to here. And this one will be Z12 is Z12 with an angle of alpha, I suppose. Uh, okay. Now when we come to forces, we see the following. Uh, the forces are, many forces are equal. That is G14 is equal to magnitude wise is equal to F34. So instead of J14, you can say F34. F13, F32 is equal to F23 is equal to, okay, F23 is equal to G12. Okay. And then that's all actually. Yeah, there's something, by the way, I forgot to mention. If you have a three-fourths number, you need to have one moment equation also here. It's not just, you cannot just get away with two-fourths equation. If you have a three-fourths number, you need all the equations. Okay. So in our case, you have number 4 is a two-fourths number. So you have no equations. Your number 3 is a three-fourths number. So you have three equations. Well, it's very small. You need three equations. And for 2, you have a two-fourths plus one moment number. You just need a one moment equation. Which means that you have three equations here, one equation here. You have to write 4 equations here in order to solve for your unknowns. Well, otherwise, all the other things we have written down here. For link 2, let me just open a new page. So if you take a moment about point O, you will have T12 minus F23 A2 sine alpha plus pi minus theta 1, 2. Well, this pi is kind of unnecessary here. This you can write as T12 minus F23A2 sine alpha minus theta equals 0. You can use the fact that sine, let's say A plus B is equal to sine A cosine B plus cosine A sine B. And you use pi as, let's say, like your A, okay? In which case sine pi would be what? 0. And cosine pi would be -1, so this would be a plus. All right. This would be 0, from which you can solve for T12. Whereas for link 3, you have, as you might remember, let me just try to remember what we had. F43 downwards, something like 43, F13, like this, and we have so we use summation of forces in the x direction is 0. Summation of the forces in the y direction is 0. And we just take a moment about some point. I don't know which point we can take. Let's say we can say take moment about point A or B equals 0. From here, solve for F 43, F 23, and angle alpha. Those are the unknowns, okay? And you solve for T12 from this equation. And you have 3 more equations which you solve for these. I'm not going to solve it in detail, but I show you how you can do it, okay? So basically the problem is solvable, as you see. I'm not going to go into the details of how you write all these things, all these equations and so on, which you can do yourselves. It's not too difficult. But I will solve something a little bit more simple, another 4-bar mechanism, which will be like this. This is kind of simpler, as you will see. So T14 is unknown and T12 given. T12 is given. So the torque on this side is given. Torque on the other side to keep the mechanism in static equilibrium is asked. Okay. We want to find the torque on the other side to keep the mechanism in static equilibrium. It's not too difficult. It is kind of similar. There is no three-force member. There are only two force and moment members here. Let's draw the free body diagrams. For example, here, this is link 2, this is link 3, and this is link 4, let's say. Well, you can start from link 3, that's the simplest one. Link 3 has the two-force member, F23 is equal to F23 with an angle of theta 13. Okay, this is as an angle of theta 13. F43 on the other hand, this one, F43 is equal to F43 with an angle of theta 13 plus pi, right? Because it's in the opposite direction. Okay, that's the two-force member. We have exhausted everything, every knowledge in that member. How about this one? Here you have well, I said F43, but that's not necessary really. I can erase this and write F23 instead, right? Let me use F23. So this is also F23 with an angle of, but I have to write the name first. F34 would be F23 with an angle of, again, theta 13, right? On the other hand, there is a torque here, T14. We don't know this, but this is these forces have to be equal in magnitude. So this is G14 is equal to F23 again, magnitude. It is theta 13 plus pi, okay, as you see. Okay, now F23 is in this direction. So F32, no, 32, 32. F23 again, with an angle of theta 13 plus pi. And we will have G12 is equal to F23 with an angle of theta 13. And also we have T12. T12 is known. So these are the free body diagrams. This is a 2-force plus 1M member. This is a 2-force member. And this is again 2-force plus 1M member. Okay. So what are the unknowns here? It's quite simple. Unknowns are, when I write it this way, is F23 is an unknown. What else? T12 is given. F23, F23, F23. Angles are known. So only T14. So two unknowns here. Well, Let's say that this point is O. If you take moments about this point, let's do it here. Link 2. Moments about point O is what? A2 vector times F32 plus C12 as a vector. C12 is clockwise. It will be, I will write a minus there. So it will be A2 times F23 times sine angle of the force is θ13 plus pi minus θ12 minus T1. What is that equal to? It's equal to 0. This is 0. This is equal to 0. Oh, okay. That's one equation. Let's say that this is our equation 1. The board is full. So, I'm trying to open up some space to write a few more things, but I cannot, so let me just open a new page. So we have to take moments for moments about for link 4. Let's say that this point is, this was O, let's say this is O4. T4 plus T4. T4. Let's say that this is our second equation. The first equation we had, remember, we had this was our first equation. So we have an expression for T12. We can solve for F23 from T12. T12 divided by A2 sine θ13 plus pi minus θ12 which you can substitute into here. Two, one. Sorry, substitute into two. Oh. From which you get T14 is equal to minus A4 over A2 T12 sine theta 1. Two. But remember that trigonometric identity, which was, where was it? Here. Sine A plus B is equal to sine A cosine B, etc. Okay. In that case, we can write this as minus sine theta 1, 2 minus theta 1, 2. Okay. If you do it, you will see that this is correct. So you can say that T14 is equal to A4 over A2 sine theta 1, 2 theta 1, 4. Times 2, 1. And that's the result. This is a nice and clean expression. And it looks similar to the expression we had for velocities, I think. I don't remember exactly, but if you have a 4-bar mechanism like this, if this is omega 2, if this is omega 4, I think the relationship between omega 1, 4 and omega 1, 2 is very similar, probably exactly something like this. Okay. Okay. One more static analysis problem I want to start. I don't know if I can finish it, but well, I'll do it rather quickly, not with all the details, so that we can do it, I hope. This is a slider crank mechanism, but an inverted one, which means that the slider is moving inside a rotating link. So it is something like this. This distance is r. It is the distance of 3 with respect to O4. And there is a force acting here, which is F14, which is known supposedly. Okay. This link length is assumed to be known. You want to is unknown. We want to find it out. So I found 4x with respect to the fourth link, and this is a right angle. Okay. As usual, we draw our free body diagrams. Okay. Well, the force acting on link four. F14 is like here, perpendicular. F34 has to be perpendicular because it's a normal force. Okay. So it is in the opposite direction. Well, we assume that it's in the opposite direction to F14. Now, what can be the direction of, let's say, whatever it is, G14? It has to be something like this, right? Or it has to be along the same line. It cannot be anything else. About link 3, what forces are there? F34 is there. There is F43. Well, what else? F34 is equal to negative F43. But there is also the force exerted by link 2 on 3, which is F23, I suppose. But what is F23? But it has to be like this because there are no other forces. It's a two-force number, F23. We understand? This is link 3, this is link 4. And then there is the link 2. So F32 has to be like this. T2 is T12 is the force, and well, I made a mistake there. Of course, this cannot be like that. It can be, but I shouldn't have drawn it like this. It's confusing. It has to be. If you draw it perpendicular, then everything looks like perpendicular, which it is not. Or maybe I should draw it like this. Okay, this is link 2. So this is T12 is unknown. Okay, let's not now try to write these down, what kind of things they are. First of all, this is a 3-force member. This is a 2-force member. This is a 2-force plus 1m member. Okay, now let's start from F14. F14 is F14 with an angle of theta 14 plus pi over 2. That's given. F14 has an angle of like theta 14. This is theta 14. Theta 14. This is theta 14. This is theta 14. So you add that pi over 2 to it. Okay, 90 degrees to it. Okay, F34 therefore is equal to F34 is with an angle of theta theta 14 minus pi over 2. And F14 G14 is G14 with an angle of again theta 14 plus pi over 2 because it's the same. Supposedly it's in the same direction with G14. F23 is We can write f two. You can say again f(3,4) with an angle of theta 1, 4 plus two. G1, 2 can be written as again f(3,4) with an angle of theta 1, 4 minus pi. Let me try to finish this as quickly as possible. For the fourth link, you can write f(1,4) plus g(1,4) equals f(3,4). Let's say that this is our first equation. And if you take moments about all 4 points, from which you can say that f(3,4) is equal to a4 over r f(1,4). So that this is our second equation. This is our third equation. Okay. Well, we have 1, 2, 3, 3 equations. And what are our unknowns? Let me write the unknowns. Where can I write? Let me write. Let's write it on a new page. Unknowns are as follows. T12 is an unknown. F(3,4) is an unknown. I have isolated everything. And G14 is an unknown. Okay. So 3 equations with 3 unknowns, as you see. G14, this is unknown. F(3,4), this is an unknown. And what was it? Something else. G12. So 3 equations, 3 unknowns, which can be solved for. And we want to solve for T12 anyway. And the solution is as follows. You can just do it and check it if you like. T12 is equal to A2, A4 over R. And that's the result for this problem. The next time we will be doing systems with resisting forces, that is with friction, systems with friction, against static analysis, and probably we will finish static analysis and go on with dynamic analysis. Okay. So that's all for today. Let me stop the recording.